We're in Chapter 4. We've covered the continuity equation for open systems. We've covered the first law of thermodynamics for any open system. Could be pretty complex. You may not even be able to get that general statement of the first law for any open system in your head. I think that's okay. I can live with that. But there's going to be a simplification of that general statement of the first law, or often used and often modeled open system called steady state, steady flow, that I hope you're kind of familiar with at this point. And so the objective of this video is to try to help you get the first law of thermodynamics for a steady state, steady flow open system into your head, so you don't have to treat that statement of the first law as a formula. The steady state, steady flow first law for open system, it's really kind of a fundamental for a large proportion of engineering problems and homework problems, quiz and test problems that you're going to encounter. So what I'd like to do is get started and see if I can help you get that statement of the first law into your head. Picking up from last time, you remember that there was equation 415 in the book, and that was the general statement of the first law. Any open system, at any time, things changing in time, things are different at lunchtime than they were at breakfast time. Things are all over the map. And then what I wanted to suggest was that you sort of change your thinking, change your look, and the way you look at this equation 415. It's the identical fundamental, but sort of figure out how to get the boundary phenomena moved over to the left-hand side of the equal sign, and then the other terms over to the right-hand side of the equal sign. At least that helped me get it into my head as best I could recall it. So I remember as an undergraduate student recalling bits and pieces of it, but I'm going to have to openly admit I had not mastered this statement of the first law. It took me to get into graduate school to get better at doing this. Now then, in the previous video, we said, okay, we've got this general statement of the first law that's a little easier to visualize. And now let's look at the situation where we have steady state, steady flow. Okay. And we looked at and studied it, and we said, well, there is one term, this dE dt of the control volume, the time derivative of the energy change in control volume, that goes to zero. And then, of course, because it's steady state, steady flow, and then we remember, oh, yeah, that's right. We also say that Q dot N, well, that's just some constant number of kilowatts, some constant number of BTUs per second, minus output power. It's operating steadily, so the output power would be so many kilowatts or megawatts, and that would be a constant value. And the same thing here on the M dots, the mass flow rates. They're those coming in and leaving, they're at a constant value. So the sum of the inflows is going to equal the sum of the outflows. Okay, and so you've got that steady state, steady flow you can get, and I'm going to suggest, so let's throw that term away and simplify our equation 415. So we've got Q dot N minus W dot out equals the sum of the M dot leaving times H enthalpy, H leaving, kinetic energy and potential energy leaving, minus the sum of the M dots in H times quantity H in kinetic energy and potential energy in. And so I was able to get, as an undergraduate student, I was able to get this into my head without the need of a formula sheet. So I got that part. Okay, so it is my hope that you can get this into your head as well and have it in accurately, so you don't get things confused, and you're able to quickly write that down when you encounter a problem that is open system, steady state, steady flow. So I hope you can get that, write that down. All right. So we have simplified the general statement to something that is actionable for steady state, steady flow, open systems or control volumes. Now let's simplify again. Let's say, now this is going to be very common, that you've got an open system where you have only one inlet and one outlet, kind of like a steam turbine or a gas turbine engine. There's lots of examples where you've got steady state, steady flow with one inlet and one outlet, and we should have the continuity equation in our head already, right? Continuity equation says m dot in equals m dot leaving. Well, wait a minute. Since they're both equal, when we have an engineering problem to solve, let's just call that m dot. M dot. So we don't have you don't even have to have the subscript I and E for one inlet, one outlet, do you? All right. I hope you can get this in your head. Here's the first law. Open system, steady state, steady flow with all these sum signs and all that stuff. Wow. Well, if you've only got one m dot, do you see that you can get rid of these I's and E's on the m dots? You got to keep the enthalpy terms I and E, but do you see that you can group, or this is exactly the same as this. So you've got one m dot, and so on the right-hand side, you've just got this bracket term that's made up of enthalpy change from exit to inlet, kinetic energy change from exit to inlet, and potential energy change from exit to inlet, okay? Exit minus inlet. Okay, so that's the simplification. And now all of a sudden, here's you. And so I'm going to suggest that if you've got this in your head, you can quickly generate this statement of the first law, steady state, steady flow, one inlet, one outlet. It's almost like you don't even have to have that one in your head. See, you certainly don't have to put it on a formula sheet, because you can quickly get to this fundamental from this one. I hope you see that. And I hope you're spending some time thinking about, how do I get these fundamental relationships in my head so I don't have to depend on a formula sheet? So I'll have to tell you, we don't see practicing engineers walking around with formula sheets or electronic sheets on their tablets or things like that. Practicing engineers have these fundamentals in their heads. Here's another little technique I'd like to suggest. I'd like to throw out for you to compare. Trying to move my picture around here. Let's compare steady state, steady flow, open system, one inlet, one outlet. So here's my sketch. Let's compare that to what you already know about a closed system problem, kind of like a piston and cylinder, closed system. So we just came up with this. So this upper part of the slide, we just talked about open system sketch, one inlet, one exit. So the state going in is I, and the state leaving is E here on my sketch. And so I've just got one m dot, because it's steady state, steady flow. So Q dot in minus W dot out equals m dot times a bracket term, HE minus HI, this outlet state minus inlet state. Enthalpy change, kinetic energy change, and potential energy change. Now let's compare. Let's think about what you have in your head now. Okay, here's my closed system sketch. There's my system, right, with my dash line. It's a substance contained within a piston and cylinder. I'm changing states from 1 to 2. I'm going through a process 1 to 2, process 1 to 2. Okay, slowly, quasi-equilibrium process. And boy, I really hope that you don't need to go back to a formula sheet to remember that Q in minus W out equals the change in energy E. And remember, the change in energy E was made up of delta capital U plus delta capital kinetic energy, change in potential energy. And then remember that we early on, second week of class, we said, well, delta capital U is the mass M times delta little u. You remember that, okay? And so this should come to out of your head pretty quickly. Qn minus W out equals M, the mass of the closed system, times U2 minus U1 plus kinetic energy 2 minus 1, potential energy change 2 minus 1. Wow. Now visually, have a look. Look up and down. Look above the red bar and below the red bar. Look how similar those two statements of the first law look. On the upper side, for open system, I see dots over the Q and W and the M. Well, it's all about the dots for open systems. That must mean a rate, mass flow rate, a rate of heat transfer, power. Down below, there's no dots, right? But look how similar it looks. Now, the important thing I want you to see for this video is things look similar, but things also, so look at kinetic energy terms. Well, they're similar, aren't they? Potential energy, similar. And so in many of your homework problems and sketches will be provided. So do be aware that instead you're going to go from a cloud to a real piece of equipment. Also, typically E might be labeled state 2 and I might be labeled state 1. So do you see in this fundamental, do you see that E and I could become 2 and 1? You see that? Okay. And this is where a lot of students get confused, especially those students that depend on formula sheets, because some on their formula sheet, they're going to put m dot times the quantity H2 minus H1. But then down here, they've got m times the quantity U2 minus U1. And then they get in a high stress situation and I say, uh-oh, what formula do I use? I don't remember what formula you use. And they get all excited and the result is poor performance. And so again, what I'm trying to convince you of is getting things into your head, understanding what they apply to, but look at this difference. Look at this difference for an open system where you're looking at enthalpy change compared to a closed system where you're looking at internal energy change. That is an important difference for you to recognize. And it's not just a careless error. So when anybody is reviewing your work on a quiz or a test or exam, if you start using internal energy change up here for an open system, you're going to get murdered. Okay. Similarly, if you start using enthalpy down here for a closed system, you're going to get murdered. And so please be aware of that. Okay. And so on the positive side, look at the similarities to help you get things into your head. Similarities, differences. When we've got an open system, we're using enthalpy change. When we've got a closed system, we're using internal energy change. And you remember the difference back to the sort of the lectures, the enthalpy change is the result of flow work that is done on the fluid that's flowing into and out of the open system. So this little slide, and that's the purpose of some additional videos that I'm going to offer and remind you of that you may wish to look to really try to cement this into your heads to really understand the difference in the fundamentals between an open system and a closed system. And so these are these two videos that I would recommend. Here we go. How are you going to remember all these formulas? Gosh, I've only allowed one sheet of paper from a formula sheet. How am I going to keep all this stuff straight? So try to figure out how to keep this stuff straight in your head. So two videos that I recommend is my first law crash course, as well as my comparison of open systems to closed systems. And you can find these in my Thermodynamics Fundamentals playlist. Now, in these videos of chapter key points, you're seeing that I'm not really working out any problems, but I try to work out problems that I've selected for each chapter. And for chapter 4, I've got 2 problems that I've worked out start to finish, and I explain how did I do the solution for these two open systems from chapter 4? They're totally different types, but both of these homework problems are steady state, steady flow, open systems, and both of them have one inlet and one outlet. And so if you have a look at those problem solutions, that might help you put it all together to go from fundamentals, governing equations into, okay, now how do I put numbers into these fundamentals to get a numerical result? So both of these are pretty decent homework problems that I didn't pick these just at random. I picked them to be representative of open system, steady state, steady flow, one inlet and one outlet. So let's recap what we just covered. You have the ability now to simplify the general statement of the first law for any open system and hopefully get that into your head. So it's my hope that you spend a little time getting these fundamentals into your head. We just went through an example where you compared the first law statements of a steady state, steady flow, open system, one inlet, one outlet, and you compared that to a closed system. And I tried to show you how are they similar and how are they different. And that's a key. So that's a key thing to understand and have at the top of your head so that you can perform well on quizzes, tests, and the exam, and you can prepare yourself to be a practicing engineer as well. In the next video, I don't want to leave you high and dry and have you thinking that all homework problems and all engineering problems are steady state, steady flow, open systems. There's another category of open systems and that the textbook calls transient flow. And I want to give you some specifics about how to attack a more general first law open system problem that's considered transient flow. So I'll give you some details about that in the next video. Some sections will cover this transient flow situation, and some sections may not. It all depends on the priorities of your professor or instructor and how much time is available and how fast your class is making progress in mastering the fundamentals. So I hope that helps, and stay tuned for the next video where I'm going to try to cover some of the highlights of numerically evaluating a transient flow open system problem.